Yes, thank you very much. Uh, yes, I'm going to speak about the producing of the single crystalline lithium manganese oxide spinel cathode materials for lithium-ion batteries. Then the aim of our work to produce the nanocomposite materials by reinforcing the reduced graphene oxide. And this is a view from our campus, the Sakarya University in Turkey. Yes, in Sakarya University we have a group. The name of group is Lithium-Ion Battery Development and Application Center. In our center, we are studying on the lithium-ion, lithium air flow and sodium-ion batteries. We are mainly concentrated on the developing null anode cathode materials and also studying on the new electrolyte materials. And also we have a subgroup that's working on the computational studies. Then if you are familiar to lithium-ion batteries, there are some of the commercial cathode materials. Then here in this table, I have tried to show this commercial cathode materials. Among these commercial cathode materials, lithium manganese oxide, which is shown here as LMOI, has the best cost performance because if you look at the capacity and working voltage and the energy density, and also if you compare with the price, it is a commercially best cost performance material among the other cathode materials. If we look at this lithium manganese oxide LMO materials, in regular LMO materials, the capacity is approximately 120 ampere hour per kilogram. And also we have some instability problems. For solving this, the new group is the high voltage spinel materials. And in the spinel materials, it is aimed to dope the lithium manganese oxide by using the nickel or chromium, like this type of the materials. Then by doing this, the capacity can be increased to 140 ampere hour per kilogram with increased voltage window range. So if we look at the LMO properties, yes, it is cheap. Then the cost is low when compared with the other cathode materials, but we have some of the difficulties. The first one is the Jahn-Teller distortion. The solution of the manganese into the electrolyte and decrease the stability of the electrode. And the other one is the transformation of the cubic phase to the tetragonal phase. And another disadvantage is the low ionic diffusion in this cathode materials. For solving this in the literature or in the commercial area, people are trying to propose different approximations. And here you can see the summary of this approximation using the nanoparticles or 1D nanowires or doping the cathode material with different elements and coating the surfaces of the lithium manganese oxide with the conductive metals and some of the ceramic materials, or producing these materials in the type of the composites to increase the conductivity and stability, and also producing the new hybrid structures with a special architectures. In our approximation, we have aimed to use these two last techniques, to use composites and to produce the nano architectures. We know, I'm not going to concentrate on this matter, but we know when we look at the nanocarbons, there are several applications area, and energy storage application is one of these application areas. And we have started to use the alpha manganese oxide material productions, nanowire production, because we have aimed to use the alpha manganese oxide nanowires as a template. We produce these materials by using the microwave hydrothermal synthesis. You can see these precursors and the treatment temperatures after production. We have the manganese oxide nanowires with 20 and 50 nanometer radius, and their length is approximately 2 and 3 micrometers. And we have used the as alpha manganese oxide as template. Then we have used the solid state reactions by using the lithium hydroxide and the chromium acetate. After the grinding of this materials and heat treatment, then we have produced the lithium manganese oxide nanowires and lithium chromium manganese oxide nanowires. And the last step is the producing the freestanding electrodes. Then we have mixed the graphene oxide together with the LMO materials, nanowires, and we have decorated the nanowires between the graphene layers, reduced graphene oxide layers. Then you can see the thickness of our freestanding electrodes. And this is the high magnification microstructures. Then you can see the nanowires that decorated between the reduced graphene oxide layers. So these are the XRD analysis. You can see by adding the chromium and the shifting of the 110 peak to the left, which is showing the increasing the compressive stresses. Then we have reduced the lattice parameter, which is we are expected to increase the stability of the electrodes. Then this is the regular Raman spectroscopy for the graphite and graphene oxide and reduced graphene oxide. And these are the LMO, lithium manganese oxide, and chromium doped lithium manganese oxide, increasing the peaks, showing the increasing the conductivity of our electrodes. And also, if we have introduced the, if we have produced the LMO or LCMO decorated graphene, then we can increase the absorbance level of our electrodes. And these are the scanning electron microscopy structures: alpha manganese oxide, lithium manganese oxide, and lithium cobalt manganese, chromium manganese oxide. You can see very homogeneous size of the diameter of the nanoparticles, nanowires, and this is the graphene and graphene freestanding electrode cross section. We have also carried out the transmission electron microscopy studies. You can see here, it's not maybe clear here, but this is the lithium chromium manganese oxide, then decorated on the surface of the reduced graphene oxide. We can see by doping chromium, then the lattice distance, the lattice parameter is decreasing. This is scanning electron microscopy cross-sectional structure showing homogeneous distribution of our components. And also we have carried out the electrochemical tests. So we have not enough time. I am also going to summarize by adding the chromium and by mixing the graphene, reduced graphene oxide. Maybe the first discharge capacity is approximately the same, but after 220 cycles, we have almost 120 milliamperes per gram capacity, which is very good for this cycle number. And this is the comparison of the discharge capacity with the cycle number when we have doped chromium and we produced another composite with the graphene oxide. We have very stable capacity after 200 milliamperes per gram, and also 200 cycles. And also, if you look at the impedance analysis results, introducing the chromium and producing the nanocomposite reduced the charge transfer resistance of our electrodes. So in summary, chromium doping improves the capacity and stability because it is preventing the lattice distortion, and producing a nanowire lithium chromium manganese oxide, graphene oxide cathodes. We have high discharge capacity, and nanocarbon, especially reduced graphene oxide, entrapment or decoration of this electroactive material decrease the lattice distortion in our electrodes. And also I want to, thanks to Cost Action for this activity, and also TÜBİTAK to support our project. Thank you.